Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you've come to the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. I'm going to talk about limits of multivariable functions along a path. What that means is I'm going to use a path as an aid to compute these multivariable functions, and in particular I'm going to focus on proving that certain limits do not exist. First and foremost, let me remind you back from Calc 1. Suppose I had the following scenario. I've got a graph of a function where, let's say at x equal to a, where let's say I have this and then I've got that. So I have a what's called a jump discontinuity, right? If I wanted to look at the limit of f of x as x approaches a, well, that limit does not exist because the left-hand limit and the right-hand limit are different. That means if I approach the values of a from the left, then the left-hand limit is going to be the y value corresponding to this open hole. And if I approach from the right-hand limit is going to be the y value corresponding to this open circle right here. And since the left-hand limit and the right-hand limit are not the same, the limit does not exist. Now, is there some sort of an analogous idea in Calc 3 when I've got multivariable functions? So, of course, there is. Here's the difference. In Calc 3, we are going to look at not the limit of a single variable function, but we are going to look at the limit of a multivariable function. And that means that I've got an ordered pair is going to approach an ordered pair. Now, over here, we had a left-hand limit and a right-hand limit. And in order for the limit to exist, both of those had to be the same. So here's the question. How does this ordered pair approach AB? Well, let's get a picture. If I look at, actually, I don't think this screen one shows up. Maybe was it this one that was better? Yeah, it's about the same. All right, so let's say AB is some point over here. Right, so this is my ordered pair AB. How can the ordered pair inputs XY approach that? Well, they could approach it, certainly by a straight line. They could approach it using some sort of a, say, parabola. We could use a trig function, exponential function, logarithmic function. Any function or that gives me a graph that passes through that point, that's a way that we can approach that. And in order for this limit to exist, it has to be completely irrelevant, or the value has to be independent of how I approach AB, just like it was over here. The left and the right-hand limit, we could say that those are limits along this path or this path, whereas up here we're taking a limit along this path or whatever path I want to consider. And once again, in order for the limit to exist, it has to be independent of the path used to approach that point. So what I'm going to do is I'm going to show you an example of a multivariable function or a multivariable limit where we're going to use two different paths to demonstrate that the limit does not exist. So let's take a look at the following. Let's consider the limit as xy approaches the origin of the following expression. X to the sixth plus 3y squared. Let's do, yep, and then on the top, let's do, let me think about that to make this work. x cubed y. Okay. Certainly I cannot plug 0 into that, and so therefore I have to do something, some sort of manipulation. Notice that the denominator isn't going to factor, so I can't try to do some sort of algebraic manipulation. So what I'm going to do is I'm going to compute the limit along two different paths. And the idea is I want to demonstrate that the limit does not exist. So compute the limit along two different paths to demonstrate or to show that the limit doesn't exist. Okay. So I'll show you how to find paths and then how to work with that. All right. So I have the following. Here's x-axis, here's the y-axis, and I'm going to approach the origin, right? And so I can approach the origin different ways. First and foremost, let's pick a very simple path. Let's take the path y equal to 0. So the path y equal to 0 is, in other words, the x-axis. So I'm going to approach this way. And I'll call this, again, this is going to be path 1 is y equal to 0. So let me show you how to compute that limit along the path. Now first of all, again, I can take any function that I want, y equals f of x, which passes through that point. Again, I'm picking a very simple one, y equal to 0, and that does pass through that point. In other words, like I can't use the path y equal to 1 because that doesn't pass through the origin. Now here's how we compute the limit. So the notation is I'm going to write the limit of x cubed y over x to the 6th plus 3y squared as xy approaches the origin, and I'm going to denote the path underneath, so y equal to 0. Okay. Now the way I do this is I'm going to substitute the path into this expression, which is going to turn this into a single variable expression. Then I'm going to replace this multivariable notation here with a single variable notation because y is fixed at 0. And the only thing that I need is x approaches 0. So let's go ahead and plug that in. This would be the limit as x approaches 0 of x to the 3rd times 0 over x to the 6th plus 3 times 0 squared. Now, notice in the numerator, I'm multiplying by 0. Anything times 0 is 0, and so this whole in the denominator is not 0, and therefore this expression is identically equal to 0, except at 0, but it's identically equal to 0 as we're approaching 0, and so the limit of the constant is that constant, and so this is 0. So along the path y equal to 0, the limit is 0. Now, let's pick a different path. So path 2. Now, before I tell you what the path is going to be, let's take a look at this expression. Once again, I can't factor it, I can't cancel anything, but now I have this sort of freedom where I can replace y with something. And as long as it goes that y equal to expression, that function passed through the origin, I've got complete freedom to choose something. So let's choose something convenient. Well, what would be really convenient is if I could combine the denominator terms into one term. Well, so since I'm able to choose something to replace the 3y squared, what could I do to that so that it could get turned into something that would then combine with the x to the 6th? In other words, I would need something of the form something times x to the 6th. Well, if I replace y with a power of x, then a power to a power, you multiply, so as long as that product becomes 6, then this can become one term. Well, therefore, there's only one choice. Y would have to be x to the third, or 2x to the third, 3x to the third, 4x to the third, a constant times x to the third. But let's just choose x to the third. So my second path is going to be y is equal to x to the third. Let's go ahead and then compute the limit along that path. Okay, so I would have the limit as xy approaches the origin along the path y equals x to the third. Now I squeeze that in there. I don't know if you can even see that, but it's the same notation I did here. And then you've got the expression x cubed y over x to the 6 plus 3y squared. Now, same thing, I'm going to plug in the information for the path, meaning I'm going to replace every occurrence with y with x to the third, and then I'm going to replace this notation here, this arrow notation, which is x goes to 0. So this would be the limit as x goes to 0 of x to the third times x to the third over x to the 6th plus 3 times x cubed squared. All right, now let's go ahead and clean that up and then compute the limit. All right, in the numerator, notice I've got x to the third times x to the third, which would be x to the 6th. And then in the denominator, x cubed squared would be x to the 6th. Therefore, the bottom is 4x to the 6th. And of course, I can't plug 0 into that, but I can simplify the expression first, cancel the x to the 6th, and I get 1/4. The limit of a constant is that constant, so therefore along path 2, I get 1/4. Along the first path, I got a limit of 0. Along the second path, I get 1/4. And therefore, since those are not the same, the limit of the original expression does not exist. Okay? Thank you for watching. Please consider subscribing.